Last year, ASTRA launched its very first solid rocket, and everything went pretty well. We achieved an altitude of just over 1 kilometer, and many systems that we were testing worked out pretty well, except for our recovery system. Unfortunately, the parachutes didn't deploy, and we ended up crash landing in a field. Of course, this is not an ideal result. We definitely need to fix this if we want to realize our big vision of launching a rocket to space and recovering it successfully. So we're now developing a new rocket called Descendence, which should fix all of the problems we had on Ascendance. And we're only 2 weeks away from this launch. However, before we can get into the design changes we've made on Descendance, we first have to understand what went wrong on the last launch. Looking at our flight data and the footage from the Descendance launch, we can see that the avionics system did correctly detect apogee and initiate the recovery process. This starts with ejecting our nose cone and allowing our drogue parachute to come out. In the footage, we can see that our nose cone did indeed come off. However, you may note an absence of a drogue parachute. After further review, it was noted that our separation was not a very energetic process, and unfortunately didn't have the force to actually pull the drogue out with it. So unfortunately, the drogue parachute got stuck inside of its containment tube. Without the drogue parachute out, it was impossible for the main parachute to deploy, and so that's why we crashed in the field. The separation system we use takes advantage of a compressed CO2 cylinder, which is then allowed to expand into our nose cone, thereby pushing it off. This is triggered by opening up a valve on the hydraulic line, which is connecting to the CO2 cylinder. However, getting a very leak-tight nose cone can be quite difficult, which kind of takes away from a lot of the power that's available in the compressed gas. So for this reason, we decided to switch to using a piston cylinder, which is able to drastically reduce the amount of volume that we need to pressurize with gas, while also reducing the chances of leaks. But how does it compare to the deployment power of our past system?
Let me see that again. I didn't get a good look at that. Yeah, boy.
Right there on the recovery plate there, you can see there's this wire. That is actually nitinol. And we're going to be using that to deploy our main parachute. It basically activates by putting a current through it, and then it is able to pull on a pin that then activates our parachute deployment. Nitinol has this fantastic property where it can take on a different shape depending on whether it's being heated or not. You can stretch out the nitinol in any kind of shape you want, but then when it gets heated, it will basically return to that original shape. And we're going to take advantage of nitinol's shape change in order to pull on a pin, which then allows our main parachute to be deployed. 3, 2, 1, deploy. On our previous system, we were using a servo to perform this function, but it was a bit difficult to mechanically get that working in a reliable way. So with nitinol, we hope to solve this problem and hopefully get a very reliable main parachute deployment. And bippity boppity boom.
Oh, magic.
Nitinol may have some major mechanical advantages, but there are disadvantages too. Because the nitinol is essentially just a wire, it draws a crazy amount of current. And unfortunately, our flight computer is not really designed to handle that kind of a load. So we had to make some modifications to the electronics in order to get it all working. So this is our solution to activate the nitinol. Here you can see we have what are called giant MOSFETs. They're still pretty small in my opinion, but they're big in the world of MOSFETs, I guess.
This bad boy is a resistor
that can handle 100 volts and its resistance is 2.2 ohms. We are using it to limit the current that's coming from our battery in order to safely activate the nitinol. We have come to the conclusion that at 5 amperes this thing works with the requirements that we want from it. So we had to limit the current with this. But since 5 amperes generates a lot of energy, we needed to have a resistor that can handle that energy. That's why it has all these shiny metal parts to it, in order to dissipate the heat.
We hope that you've been enjoying all the exciting updates to our rocket Descendence, which we're going to be flying very soon. We've really been putting a lot of work into this one to make sure that it ends up being a success. But in order to build all these rockets, we need a lot of financial resources. It's not cheap building rockets and testing them and sometimes blowing them up. So that's where your support comes in. Right now we're running a crowdfunding campaign and collecting the money that we need in order to realize our dream of getting all the way to the carbon line. And of course, we want you to be part of that. We're going to be sharing updates about our mission and all of the ups and downs right here on this YouTube channel. So be sure to be there with us, and we hope to see you at the carbon line. For our last launch, we used the Cesaroni 3660 L1720 motor, which has a peak thrust of around 2 kilonewtons and a total impulse of 3.6 kilonewton seconds. This motor is important in order to make sure that we have a high enough velocity coming off the launch rail so that we're aerodynamically stable. It also helps us to achieve our goal altitude of 1 kilometer. Unfortunately, we don't have access to this motor anymore because it is out of stock.
So, Professor, would you say it's time for everyone to panic? Yes, I would, Kent.
But don't worry, all is not lost. We were able to find an Aerotech L1000 motor, which is still able to fit inside our system. Unfortunately, the total impulse that it has is only 2.7 kilonewton seconds, which is a little bit less than our Cesaroni motor. Also, more disturbingly, the maximum thrust is only 1.26 kilonewtons, which is much less than the 2 kilonewtons we were getting from the Cesaroni motor. This all points to one thing. We need to cut some mass. The Descendence rocket weighed a total of 18 kilograms, and to make this Aerotech motor work, we really need to get that mass down to about 16 kilograms. The natural first place to start are those somewhat bulky looking aluminum bulkheads. Here you can see the difference between the original bulkhead, which was very bulky, and the bulkhead with mass optimization. We just did some CNC milling out the middle, and also out of the internal components of the material itself. So now it's as light as it possibly can be. This change saved us a total of 400 grams on this one bulkhead. Another place where our design uses somewhat bulky materials is on the eye bolts that attach our parachutes to the body tube. Right now they're made out of steel and weigh just over 100 grams each, but these could be made out of carbon fiber.
It's a bold strategy, Cotton. Let's see if it pays off for them.
We made some 3D printed templates for the eye bolts and then just wrapped fibers around it. In the end, we were able to make an equivalent eye bolt that was just 25 grams. But of course we had to test to make sure that it was strong enough to handle our loads.
So today we tested our entire line configuration. We knew that the carabiners were rated and the ropes as well, but we were unsure about our swing and the eye bolts we were using. So we tested it on a drop stand where we attached multiple weights and height drops, and we figured out that our lines are suitable for launch.
Nice.
Switching our eye bolts to the carbon fiber variety saved us another 300 grams. We also made some mass optimizations to the design for the Descendence body tube. So we've actually wrapped this tube that we last did out of fiberglass, and we've put in the reinforcement layers between the hole inserts that we make. We've made that out of carbon fiber so that you can see what the layers look like underneath the fiberglass. And basically they are wrapping right around the hole, and they're giving lots of strength to that insert where the forces are going to be concentrated. And it's a lot better than drilling holes and even better than just having the insert and wrapping normally. This fancy winding strategy was actually able to save us another 300 grams. Finally, a combination of reducing the amount of piston cylinders we were using, making some optimizations to the avionics housing, and also strengthening some PLA parts with carbon fiber instead of just relying on a thicker infill, allowed us to save a whole nother kilogram off the mass of our vehicle, thus bringing us to a grand total of 16 kilograms.
Great success.
At this point, it's looking like Descendence is ready to fly. All of its systems have been tested and tested and tested again, so we're pretty confident that this will be the one that finally gets recovered successfully. Be sure to tune in a couple of weeks when we share our magnificent success. And remember to expand your horizons.
Pop in, burning like this, ain't checking my wrist. Third is my shift. Rolling all night like flicks. We look at the clips, these credits are lit. Stacking miles, I'm far away from home. I got what I wished for. Taking that risk, I'm checking my list. Marathon man, it's run legit. Can't let it slip when it's all in my grip. Talking too much, you probably not it. All that I did, calls I missed, time I spent. Yeah, that's that blood. Sweating my love.